Hey guys, so the video that follows was made by a student teacher of mine last year, Mrs. Malo. Some of you may remember her from class if you had me Mod 7 last year. The video is excellent. It's about titrations. I'm not going to change it at all. I just wanted to do this quick little intro so that you understand why it is you're not hearing my voice on this video. She did a fantastic job with it. It's really easy to understand, and hopefully you'll have a better idea of what titrations are all about. Okay, so watch the video, take good notes, and we'll see you in class.
Okay, this is the video on titrations. In this video, I'm going to both talk about how to perform a titration in the lab, but also how to do the calculations. So first, what is a titration, and why do we do it? Well, a titration is a technique where a solution of known concentration is used to determine the concentration of a second solution. The goal here then is to determine the concentration of an unknown solution. Let's take, for example, this bottle of 6 molar sodium hydroxide. Well, obviously this is our solution of known concentration. But over here we have a bottle of hydrochloric acid, and we do not know the molarity, so this is our unknown. Well, using titration and using this 6 molar sodium hydroxide, we can determine the concentration of the hydrochloric acid. An important note here is that you must know how the two compounds in the solutions will react because you need a balanced chemical equation. And in this case, we can say that we know sodium hydroxide and hydrochloric acid combine to yield water and sodium chloride. We'll come back to this equation later. First, some terminology. The solution of known concentration is referred to as the titrant, whereas the solution of unknown concentration is referred to as the analyte. Okay, how do we use a titrant to figure out the concentration of an analyte? Well, first we need to talk about the equipment. So over on the left here, you can see a classic setup for a titration. And this apparatus on top here is called a burette. A burette is basically a device that's used for dispensing measured amounts of liquid. And it does this, or you can do this, by opening and closing the stopcock that's shown here at the bottom of the burette. Down below here, we have an Erlenmeyer flask, and I'm sure you all know at this point what an Erlenmeyer flask is, but why is it important in titrations? Well, it's a good choice because you can swirl it and mix your solution without splashing. Okay, so the burette, this is important. The burette contains the titrant, which is always the solution of known concentration. And in our example, this is sodium hydroxide. In contrast, the Erlenmeyer flask always contains the analyte, the solution of unknown concentration. And again, in our example, this is hydrochloric acid. Let's go through the steps one by one. So the first step in a titration is to use a pipette or other device that can accurately measure out volumes of liquid and measure out a specific volume of analyte into the Erlenmeyer flask. The next step here is to add a pH indicator to the analyte and mix well. A pH indicator is a substance that changes color with pH, and the most common indicator that's used in acid-base titrations is phenolphthalein. Phenolphthalein is colorless in acidic solutions, but it becomes pink in basic solutions. Okay, so now we have the HCl and we have our indicator down in the Erlenmeyer flask. The next step is to fill your burette with the titrant, and again in our case this is sodium hydroxide. The last step here is to slowly release small quantities of the titrant from the burette into the Erlenmeyer flask until you see a color change. The color change tells you that the neutralization reaction between hydrochloric acid and sodium hydroxide is complete. We need to introduce some more terminology at this point. First is something called the equivalence point, and this is the point at which stoichiometrically equivalent quantities of the acid and the base are brought together. It's a fancy way of saying it's when the neutralization is complete. While in order to perform a titration, there must be some way to determine when the equivalence point has been reached. And in an acid-base titration, like the one described here, the phenolphthalein indicator dye is used for this purpose. So the end point then is the point at which you see the indicator dye change color, and this should be very close to the equivalence point. So I mentioned that phenolphthalein is colorless in acidic solution, but becomes pink in basic solutions. So let's look at this. When we add phenolphthalein to our HCl solution at the very beginning of the titration, the solution will be colorless, as shown in the left picture. We can then add sodium hydroxide from our burette until the solution barely turns from colorless to pink, as shown in the middle picture. If this is done correctly, the pale pink color will only persist for 30 seconds or so. This color change indicates that the acid has been neutralized, signaling the end of the titration. If you continue, however, to add more sodium hydroxide from the burette, then you will pass the end point. The solution will become basic, and the dye will turn a dark pink. If this happens, you've gone too far. Okay, let's talk about data collection now. So let's remember what you want to know. You want to know the concentration of that analyte that you started out with. And here's what you need to know. First, you need to know the volume of the analyte. Well, you already know this. This is simply how much you pipetted into the Erlenmeyer flask at the very beginning. You also need to know the concentration of the titrant. Well, you already know this too. In our example, this is 6 molar. Lastly, you need to know the volume of the titrant. And this is the one that you have to carefully take down as you're performing your titration. Basically, you need to determine how many mils of titrant you had to add via the burette in order to see the color change. This is your volume of titrant. Okay, let's revisit the color change one more time because this is the most important part of a titration. It's very easy to pass the endpoint if you're not careful. If done correctly, the pale pink color will only persist for 30 seconds or so, and if you see a dark pink color, you've gone too far. All right, now I want to take you through some basic calculations so that you know how to do these problems on paper. Let's say that you have a stock solution of hydrochloric acid with an unknown concentration, and you determine the concentration. In order to determine the concentration, you titrate the solution with sodium hydroxide. It takes 22.5 mils of a 6 molar sodium hydroxide to neutralize 50 mils of hydrochloric acid. Determine the concentration of HCl. So this is the kind of problem that you should know how to do, and it's actually fairly straightforward. So first, let's go back to our balanced chemical equation. This is always where you want to start out. Okay, let's look at this number, 22.5 mils. First thing you're going to want to do is convert this to liters. And in this case, this is 0.0225 liters. Okay, now let's take a look at this number. This is your molarity. And molarity, remember, is simply moles per liter. So another way of thinking about a 6 molar solution is that you have 6 moles of sodium hydroxide for every liter of sodium hydroxide. Okay, let's punch these into a mathematical formula then. If we say we have 0.0225 liters of sodium hydroxide, which came from there, and that for every liter of sodium hydroxide there are 6 moles of sodium hydroxide, and that came from there, then the units of liters of sodium hydroxide cancel out, and you can determine the number of moles of sodium hydroxide. Well, what you want to know is something about hydrochloric acid. So at this point, you want to convert moles of sodium hydroxide to moles of HCl. And of course, to do this, we use the mole ratio. Now, in this case, the ratio is 1:1, and you might be asking yourself, why bother write it? Well, it's always important to write out your mole ratios because it helps you to keep track of your units. In this case, moles of sodium hydroxide cancel out, and you should end up with moles of HCl. So if you do this calculation, you'll determine that you have 0.135 moles of HCl. But you're asked to determine the concentration of HCl, so we have to add one more step. I'm going to move these up out of our way so that we can keep going. Okay. So remember that molarity is simply moles per liters. And we just determined the number of moles, and we also already know liters. At least we know milliliters. So if we plug those in, we can say there's 0.135 moles of HCl in every 50 mils of HCl. But we should convert this to liters. And to do that, we simply say, okay, we know that there are 1,000 milliliters in every liter. And once you do this calculation, you should arrive at the conclusion that you have a 2.7 molar HCl. And that was your goal. We've now determined the concentration of HCl. So just back to the beginning to review, we had a titrant of known concentration, and we had an analyte of unknown concentration. And by doing a titration and keeping track of how much titrant it took to change that color, we were able to determine that we had a 2.7 molar solution of hydrochloric acid.